Let's talk about row echelon forms. Now, there's two core concepts here. The first of which is what's called reduced row echelon form. This is a very important type of matrix that will be useful for us time and time again throughout the class. So it turns out there are four rules that a matrix must adhere to if we're going to call it reduced row echelon form. So let's say that we're dealing with a matrix called R, and R can be any size. So what are the four rules that define reduced row echelon form? The first rule says that if there are any rows where every entry is 0, that's okay, but it has to be at the bottom of the matrix. So as you see in this matrix here, there is a row where everything equals 0, but that's okay because it's at the bottom of a matrix. Note that this rule is not saying that there has to be a row of zeros here. It's just saying that if there is a row of zeros, it must be at the bottom. The next rule here says if you look at all of the other rows, so all the rows where there's at least one entry not equal to 0, the very first non-zero entry must equal 1, and we call that entry a pivot. So if I go back to my example up here, I note that in the first row, the very first position is equal to 1. That's my first pivot in the matrix. If I go to the second row, note that it starts with 2 zeros, which is fine. But then the next entry is our first non-zero number here. It's equal to 1, so that is our second pivot. In the third row, it starts with 3 zeros. That's totally fine. But the next entry is not 0, but it's equal to 1, so that's called our third pivot here. Again, the last row is all zeros, so there won't be a pivot in that last row. Now, the next rule says that pivots must occur right and down. So every pivot must be to the right of every pivot above it. So if we look at our example here, how would I travel from the first pivot to the second pivot? Well, the direction is right and down, so that's good. What about to get from the second to the third pivot? Again, the direction of travel is right and down, so the rule passes here. So far, our example has passed all three rules. The fourth and final rule here says that all non-pivot entries in a column containing a pivot must equal 0. So there are 3 pivots in this matrix. If I go to the first one, note that every entry in that first column that's not the pivot equals 0. So the rule it passes for that first pivot. In the second pivot, every entry not equal to a pivot equals 0. And the same goes for the third pivot column. So all 4 of our rules pass for this specific matrix. So this matrix is in reduced row echelon form. One way to write this notationally is you write R equals RREF of R. Great. So let's look at more examples to see if we can intuit these 4 rules. Here is another perfectly good matrix. The first rule says if there are rows of zeros, that's okay, as long as that they're at the bottom. This matrix has 2 rows consisting solely of zeros, but they're both at the bottom, so that's fine. The first rule passes. The second rule says if you look at all of the other rows, the first non-zero entry must equal 1. Well, in the first row, the first entry is not a 0, but it equals 1, so that's our first pivot. In the second row, we start with 2 zeros, but the next entry is not 0, it's equal to 1, that's our second pivot. And then in the third row, we start with 4 zeros. The next entry is equal to 1, so we have our third pivot here. The third rule says that the pivots must cascade to the right and down. To get from the first to the second pivot, the direction is right and down, so that passes. To get from the second to third pivot, the direction is to the right and down. That's fine. So every pivot is to the right of every pivot above it. So the third rule passes. And then the fourth rule says in every pivot location, everything else in that column must equal 0. Well, for the first pivot column, that's certainly true. For the second pivot column, that's true. And for the third pivot column, that is true. So all 4 rules pass here. This matrix is in reduced row echelon form. Here's another example. So here I have a perfectly good 3 by 5 matrix. Let's go through the rules. There are no rows of zeros here, so I don't have to worry about the first rule at all. I do have 3 pivots. So I have a pivot in the first column, a pivot in the second column, and a pivot in the fourth column. The direction of travel from pivot to pivot is to the right and down, so the third rule passes. And then the fourth rule says that every entry that's not a pivot in a pivot column must equal 0. Well, the first pivot column is fine, the second pivot column is fine, but when I get to the third pivot column, I have my pivot, but directly above it, I have something other than 0. I have a 2. That single position derails the entire process. So even though most of the rules pass here, and the fourth rule mostly passes here, this matrix is not in reduced row echelon form. If that 2 were a 0, this would be in reduced row echelon form. So this one doesn't work. What about this example? In this example, there are 2 rows of zeros, but they're at the bottom, so that's fine. I have pivots, so every row other than the 0 rows has first non-zero entry equal to 1. And if I look at all of those pivot columns, the pivots are the only non-zero entries in those columns. So the first, second, and fourth rules pass here, but there's actually a problem. I think you may see it. If I wanted to travel from the second to third pivot, the direction of travel would be to the left and down, not to the right and down. The third rule doesn't pass here, so this matrix is not in reduced row echelon form. So after you do lots of these examples, it becomes somewhat intuitive to look at a matrix and decide whether or not it's in reduced row echelon form. Great. Now, if our matrix is in reduced row echelon form, there's a certain kind of analysis we can perform on the matrix. So here I have a perfectly good matrix. This one's 4 by 5, it looks, and this matrix is in reduced row echelon form. Now, the first thing that I do is I identify the pivot locations. The pivot locations here are in the first, second, and fourth columns. So one thing that happens in reduced row echelon form is there is a sort of separation of columns. Some columns have pivots, other columns don't have pivots. Columns that have pivots are called pivot columns. So in this situation, the pivot columns are columns 1, 2, and 4. Columns without a pivot are called non-pivot columns. In this situation, that would be columns 3 and 5. So if you're in reduced row echelon form, every column is either a pivot column, meaning there's a pivot in the column, or a non-pivot column, meaning there is no pivot in the column. And once we identify the locations of the pivot and non-pivot columns, this leads us to one of the most important concepts in the whole course, and this is the notion of rank. So the rank of a matrix is the number of pivot columns in the matrix. So here's our 4 by 5 example in reduced row echelon form. The number of pivots here is 3, which means there are 3 pivot columns. So in this situation, we would say that the rank of our matrix equals 3. So rank is the number of pivot columns. The nullity of a matrix in reduced row echelon form is the number of non-pivot columns. In this situation, there are 2 non-pivot columns, so we say that the nullity of this matrix is equal to 2. Rank is the number of pivot columns, nullity is the number of non-pivot columns. And if we think about it, well, every column is either a pivot column or a non-pivot column. The rank is the number of pivot columns, the nullity is the number of non-pivot columns. So if I add the rank and the nullity together, this should just give me the total number of columns. This is an extremely famous and important theorem called the Rank-Nullity theorem. The technical details say the following: if our matrix is M by N and it's in reduced row echelon form, then the rank plus the nullity always gives N, which is the number of columns. This theorem will crop up at a lot of different points in the course. This is the most obvious version of the theorem, but there are less obvious equivalent versions of this theorem that we'll state later. Now, what does the Rank-Nullity theorem do for us? It's an equation that relates 3 numbers. So if you give me any 2 of those 3 numbers, I can infer the missing third. So let's see this in action. Let's say that I have the following data here. Let's say that in arrow notation, my matrix R goes from R5 to R9, and let's say that someone tells me the rank of this matrix is 2. Well, remember, saying that R goes from R5 to R9 is the same thing as saying that R is a 9 by 5 matrix. Number of columns is 5, so what should the nullity be? Well, the nullity should be the number of columns minus the rank. The number of columns here is 5, the rank is 2, so the nullity of this matrix is 5 minus 2, which is 3. Here's a different situation. So let's say in arrow notation, R goes from R12 to R7. Let's say we don't know the rank, but we know the nullity. Let's say we know the nullity is 9. Well, this arrow notation is the same thing as saying that this matrix is 7 by 12, so there's 12 columns here. What should the rank be? According to the rank-nullity theorem, it should be number of columns minus the nullity. Well, number of columns is 12, 12 minus 9 equals 3. Here is a third example. Let's say that I had a matrix R, and in arrow notation, I didn't know what I was allowed to multiply R by, but I knew that when I do multiply R by something, I produce a vector in R6. Let's say in addition to having this information, I knew the rank and the nullity. Let's say I knew the rank was 5 and the nullity was 3. Well, this arrow notation is the same thing as saying that we know this matrix has 6 rows, but we don't know the number of columns. Well, that's okay, because I have the rank and the nullity, and I know that the rank plus the nullity always equals the number of columns. Well, the rank is 5 and the nullity is 3, so 5 plus 3 is 8. That's telling me that the number of columns here, in order for this data to make sense, has to equal 8. So the power of the rank-nullity theorem is that if you're missing one of these 3 pieces of information, the rank-nullity theorem allows you to recover that missing piece of information. Okay. Now, if a matrix is in reduced row echelon form, if we study the pivot columns and the non-pivot columns, what we realize is that there are relationships between them. The pivot columns are very simple vectors. There's a 1 in one of the positions and 0 is everywhere else. So it turns out that if you're in reduced row echelon form, every non-pivot column can be reached by taking linear combinations of the pivot columns coming before it. Let's see that play out in this example. So here I have a 4 by 5 matrix in reduced row echelon form, and the pivot columns are in columns 1, 2, and 4. So pivot columns here are columns 1, 2, 4. The non-pivot columns are columns 3 and 5. Well, if I look at column 3 here, that's the first non-pivot column, the coordinates are -3, 7, and then 2 zeros. If I look at the pivot columns coming before column 3, what I realized that if I scale the first by -3 and the second by 7, that would give me a linear combination producing the third column here. So the first non-pivot column, that's column 3, is -3 times column 1 plus 7 times column 2. So that's a successful way to express this first non-pivot column as a linear combination of the pivot columns. The second non-pivot column here is column 5. The coordinates in column 5 are -9, -4, 1. Well, if I use those as the weights, then in a linear combination, and the vectors are as the pivot columns, that expresses my column 5 here as a linear combination of the pivot columns. So if I scaled the first column here by -9, the second by -4, and the third by 1, that gives me column 5 as a linear combination of the pivot columns. So when we go through this process, I like to call these new equations column relations. The non-pivot columns can always be reached by taking linear combinations of the pivot columns. And so the thing to pay attention to here is that each non-pivot column contributes a column relation. For this example, the first non-pivot column is the second column, and the second column is simply 5 times the first. The second non-pivot column is column 5. The column relation we get here is column 5 is 3 times column 1 minus 8 times column 3 plus 9 times column 4. So every non-pivot column here is contributing a column relation, and remember, the number of non-pivot columns is the nullity of our matrix. So the number of column relations is the same thing as the nullity of our matrix. Now, something interesting happens if we take a deeper dive here. So let's say that I write down my column relations from a matrix in reduced row echelon form. So this reduced row echelon form matrix is 3 by 5. The pivots are in columns 1, 3, and 4, which means I have 2 non-pivot columns, and these 2 non-pivot columns give me column relations. The first column relation is column 2 equals 5 times column 1, and the second column relation is column 5 is 3 times column 1 minus 8 times column 3 plus 9 times column 4. Well, what I'm going to do here is I'm going to take these 2 equations and rearrange them so that everything is on one side. So the first equation says column 2 is 5 times column 1. I'm going to move the right-hand side, 5 times column 1, to the left, and this gives me a linear combination of the columns equaling 0. Negative 5 times column 1 plus column 2 equals 0. If I go to the second column relation and take everything to the right of the equal sign and move it to the other side, this gives me another equation. Negative 3 times column 1 plus 8 times column 3 minus 9 times column 4 plus column 5 equals 0. So the column relations have now been re-articulated as linear combinations of the columns of our matrix equaling the 0 vector. And if I wanted to, I can reinterpret those two equations as matrix vector products. What this is saying is that they are linear combinations of the columns of our matrix R that produce the 0 vector. In the first equation, the weights on the columns are negative 5 for column 1, and then 1 for column 2, and zeros for the other columns. So this first column relation can be articulated as saying our matrix R multiplied by the vector negative 5, 1, 0, 0, 0 equals the 0 vector. I can play the same game with the second equation here. This is a linear combination of the columns of our matrix R. The weight for column 1 is negative 3. The weight for column 3 is 8. For column 4, the weight is negative 9. And for column 5, the weight is 1. Of course, column 2 is not in the equation, which means its weight is 0. So what that's telling me is that if I took this matrix R and multiplied by the vector negative 3, 0, 8, negative 9, 1, this should produce the 0 vector. So this is interpreting the column relations on the level of matrix vector multiplication. Okay, so that's reduced row echelon form. This leads us to a slightly more forgiving concept of just row echelon form. So what are the rules for row echelon form? Well, if I have any matrix, the rules for row echelon form say the following. The first rule is the same as the rule for reduced row echelon form. We're allowed to have rows of zeros, but those rows of zeros always have to occur at the bottom of the matrix. For this example, there's one row of zeros, but it's at the bottom, so that's okay. The second rule for row echelon form says that the first non-zero entry of all of the rows that aren't the 0 row can start with any number. So they don't have to equal 1, but we still call them pivots. So in the first row here, the first non-zero entry is 9. That's acceptable if we're not working with reduced row echelon form. So the first pivot here equals 9. If I go to the second row, I start with 2 zeros, which is fine, and then my first non-zero number is 3. Here we would simply just say 3 is the second pivot. My third pivot is occurring here in column 4, and it equals 6. So that's our first situation where the rule is a little bit more laxed if I'm just saying that a matrix is in row echelon form, and I'm not saying it's reduced row echelon form. I still need pivots, but those pivots aren't forced to equal 1 anymore. The third rule is exactly the same as before. To jump from pivot to pivot, working your way down, the direction must be to the right and down. This matrix certainly passes that third rule. And the fourth rule is almost the same as the previous fourth rule, except here we are no longer requiring that entries above pivots equal 0, but we still require that entries below pivots equal 0. So every entry below the first pivot, you'll notice here, equals 0. That's good. Every entry below the second pivot here equals 0. That's good. And every entry below the third pivot here equals 0. That's good. So this matrix is in row echelon form, even though the pivots don't equal 1, and then in that entries above pivots don't necessarily equal 0. That's the difference between row echelon form and reduced row echelon form. Now this is one of the things where there's a relationship. Every reduced row echelon form is in row echelon form, but there are plenty of row echelon form matrices that aren't in reduced row echelon form. So in this situation, this matrix we're studying is not in reduced row echelon form. The pivots don't equal 1s, and there are non-zero entries above pivots. Nonetheless, this is in row echelon form, so we would say this matrix is in non-reduced row echelon form. Let's do some examples. So here I have a perfectly good, rather large matrix. There are rows of zeros in this matrix, but they occur at the bottom. That's fine. I do have pivots here, but they're not equal to 1. So this is not in reduced row echelon form, but we're still on track to be row echelon form. The direction of travel from pivot to pivot is right and down here, so that's fine. The third rule passes. And you'll note that every entry below a pivot here equals 0. There are some non-zero entries above my pivots, but I don't care about that. So this matrix is not reduced row echelon form, but it is in row echelon form. Here's another example. So here I have a row of zeros, but it's at the bottom. That's fine. I have 3 pivots, and their values are 2, 3, and -4. That's acceptable. My direction of travel from pivot to pivot is right and down, so the third rule passes. And once again, every entry below a pivot equals 0. This is another example of a matrix that's in row echelon form, but this is not reduced row echelon form. Here's another example. I have rows of zeros at the bottom. I have pivot values. Those values are 5, 5, 8, and 11. You'll notice that the entries below each pivot are all equal to 0. But you'll notice that the direction of travel from the second to third pivot is to the left and down. So this matrix is not in row echelon form. Great. Now, one thing to take note of is that if our matrix is in row echelon form, the analysis and adjectives that we developed previously totally carry over. What is the rank of a matrix that's in row echelon form? It's the number of pivot columns. So here I have 3 pivots in this row echelon form matrix. That means there are 3 pivot columns, so the rank is 3. In this matrix, there are 2 non-pivot columns, so the nullity of this matrix is equal to 2. So rank and nullity totally make sense, even if we're not reduced row echelon form, just row echelon form. But one thing that is unfortunately true is that the column relations are much more difficult to decipher. So the first non-pivot column here is column 3. It is always possible to express column 3 as a linear combination of the pivot columns, but because I don't have the full structure of reduced row echelon form, those relationships are much more difficult to figure out. So that's all I have to say here. I do want to call your attention to the web page where I have some Sage modules. The first calculator here will simply tell you whether or not the matrix you input is in reduced row echelon form. So if I click evaluate here, it'll print out the matrix that I've defined, so I can verify whether or not I made a mistake, and it'll tell me whether or not that this matrix is in reduced row echelon form or not in reduced row echelon form. This matrix looks like it has 3 pivots. They cascade down into the right. There is a row of zeros, but it's at the bottom, and the pivots are the only non-zero entries in their respective columns. This matrix is in reduced row echelon form. It wouldn't be terribly difficult to derail this example. If I set this 1, 3 entry equal to anything other than 0, so let's say I made it equal to 1, this matrix would no longer be reduced row echelon form, so it prints out false. Sage will calculate the rank and the nullity of a reduced row echelon matrix for you. Remember, rank is the number of pivot columns, nullity is the number of non-pivot columns. Sage uses the syntax write nullity for this. If I click evaluate, if my matrix is in reduced row echelon form, it will tell me the rank, that's the number of pivot columns, and the nullity, number of non-pivot columns. I've also written some code here that will tell you whether or not your matrix is in ordinary row echelon form, so not necessarily reduced. So here I've predefined a matrix. Note that it has a row of zeros, but it's at the bottom. I have 3 pivots. Their values are 2, 3, and -4. They cascade to the right and down, so that's fine. And every entry below a pivot here equals 0. So this matrix is in row echelon form, and my code is telling me that. Once again, it wouldn't be terribly difficult to derail this process. If I set this 2-1 entry equal to anything other than 0, that would do the trick. So let's set that equal to like -17. If I click evaluate here, assuming my code works, yeah, so this matrix is no longer in reduced row echelon form because my first pivot has a